So, we talk a ton about capturing carbon dioxide, right? But the solutions, well, they're usually incredibly energy hungry. Today, we're going to break down a brand new approach from a paper in Nature Energy that offers a surprisingly clever, almost elegant way to clean the air. And this whole breakthrough really boils down to a central paradox. How in the world do you clean the air when the air itself is getting in the way and, breaking your machine? It sounds kind of impossible, but that's the puzzle we're going to unpack today. All right, so first things first, let's set the stage. The biggest hurdle in this field has always been the high cost of capturing CO2. And I'm not just talking about the price tag of the machines. I'm talking about the massive amount of energy they need to actually pull that carbon out of the atmosphere. And that's where this technology called direct air capture, or DAC, comes into play. It's pretty much exactly what it sounds like. It's a whole process designed to literally grab CO2 right out of the ambient air to help fight climate change. Now, DAC usually comes in two main flavors, and you can see them compared right here. On one side, you've got your traditional methods. These things use a ton of heat. We're talking like 900 degrees Celsius, and the energy cost, it's through the roof. Sometimes over 400 kilojoules for every mole of CO2 you capture. But then there's this other idea, the electrochemical method. This one's way cooler. It just uses electricity, it can run at room temperature, and in theory, it needs way less energy. It's the clear winner, on paper at least. But yeah, you knew there was a but coming, right? There's a catch. And it's not a small one, it's a big one. This super promising electrical method, it's had a fatal flaw. And that fatal flaw, it all comes down to a molecule that makes up 21% of the air we breathe, oxygen. Yep, let's dig into what we're calling the oxygen problem. Okay, so here's the deal. These electrochemical systems are supposed to work using these special molecules that act kind of like a chemical sponge. You zap it with electricity, and that makes the sponge thirsty. It really wants to soak up CO2. But here's the problem. The oxygen that's just floating around in the air, it attacks these very molecules. And that attack just wastes a ton of electricity and basically stops the whole process dead in its tracks. Think about it. The machine trying to clean the air is literally being poisoned by the air itself. Crazy, right? So how do you solve something like that? For years, scientists were trying to invent new, super strong oxygen-proof molecules. But this new research, it took a completely different path. And this, right here, is the aha moment. The solution wasn't some new fancy chemistry, it was just a simple, really clever separation. And you can see the whole idea right here in this diagram. It's brilliant. Instead of making a new chemical, they just redesigned the box. The big idea is just keep the sensitive parts of the machine physically away from the air they're trying to clean. It's an engineering fix, not a chemistry one. So simple. The official term for this is spatial isolation. And all it means is it's a design strategy where you physically separate the components that are sensitive to oxygen, that's the solid electrode, from the part of the system that actually has to touch the open air, which is this liquid absorbent. Okay, so we get the concept, right? But how does this clever design actually work in practice? Let's walk through the whole capture cycle step by step. So it's basically a three-step dance. First step, step one, charge. You hit the solid electrode with electricity. Remember, it's safely tucked away. This makes a separate liquid solution super alkaline, which gets it all primed and ready to grab CO2. Then comes step two, capture. That alkaline liquid gets pumped into a completely different tank. There, it's exposed to the air, and it just soaks up CO2 like a sponge. All the while, that sensitive electrode is safe and sound. Finally, step three, release. The liquid, which is now full of CO2, gets pumped back to the electrode. You just reverse the electricity, the liquid turns acidic, and poof, it releases all that CO2 as a pure concentrated gas, all ready to be stored or used. Charge, capture, release. Simple as that. And if we look at the diagram again, you can really see this whole thing in action. See? During that capture phase, the blue liquid is out there in the open, doing all the heavy lifting. Meanwhile, that purple electrode, the part that's really vulnerable, is completely isolated, safe inside the main cell. It's so simple, but it's absolutely brilliant. Okay, so the theory is great, but does it actually work? Let's look at the numbers because this is where things get really impressive. First off, the system showed a coulombic efficiency of 99%. Wow. Now, in simple terms, that just means that pretty much zero electricity was wasted fighting off oxygen. That spatial isolation strategy, it worked. Like, perfectly. And what about the big question? The total energy cost? Well, the system used just 104 kilojoules for every mole of CO2 it captured. Now, a mole is just a standard way chemists count molecules, so don't get hung up on that. Just focus on that number, 104. That is an incredibly low number. Let me show you just how low it really is. This bar chart says it all. Check it out. The new hybrid cell clocks in at a tiny 104 kilojoules per mole. Now, look at the traditional methods. They average around 375. That is a huge leap in efficiency. We're not talking about a small improvement here. This is a potential game changer for the entire economics of direct air capture. So, what's the big takeaway here? It's that this is more than just one cool new device. This is a whole new way of thinking about this kind of problem. You know, the researchers themselves say it best in their conclusion. They write, the hybrid cell design strategy of isolating vulnerable species could be broadly applicable to avoiding undesirable side reactions in other electrochemical devices. See what they're saying? They're not just saying, hey, we built a better mousetrap. They're saying they've discovered a whole new principle for building all kinds of traps. And that leaves us with a really fascinating thought to chew on. What other really complex chemical problems could be solved not by spending decades trying to invent some revolutionary new molecule, but just by designing a smarter box?